Welcome to the Deep Dive. Today, we're tackling a word that sounds pretty scientific, hygroscopicity. But honestly, its effects are everywhere. Think your kitchen cupboards, medicine cabinet, maybe even the salt shaker. It's all about this hidden thirst materials have.
It's a good way to put it.
So what is hygroscopicity exactly? How does it work?
Yeah, it's a great question. Basically, it's the ability of a substance to grab moisture, specifically water vapor, right out of the air.
Just pulls it from the atmosphere?
Exactly. And it's not passive. You know, the material has this like chemical or physical pull and affinity for water molecules.
Okay.
So the water molecules either stick onto the surface, that's absorption, or they actually get pulled into the material itself. Absorption.
Absorption on the surface, absorption into it. Got it.
And our mission today, really, is to understand how we classify this and why it's so critical, especially when we talk about things like pharmaceuticals, product quality, safety.
Right, because that seems like where this hidden property could have some major impacts. So how do scientists classify how thirsty a material is? Is there like a standard scale?
There is, yeah. Several, actually. The European Pharmacopoeia uses a pretty common one.
Okay, how does that work?
They basically measure how much weight a material gains. They put it in a controlled environment, 25 degrees Celsius, 80% relative humidity for 24 hours.
So fairly humid conditions.
Very humid, yeah. And then they see how much heavier it got.
And what are the categories?
Well, if it gains 0.2% mass or less, it's considered non-hygroscopic, not really thirsty at all.
Okay.
If the gain is between 0.2% and 2%, it's slightly hygroscopic. Then you have hygroscopic, which is between 2% and 15% weight gain.
Wow, 15% is quite a bit of water weight.
It is. And anything over that, over 15%, is classified as very hygroscopic. It shows how even a small percentage increase can shift the classification.
That really puts it on a spectrum. Now, I remember reading about another system, Callahan. Does that one take it even further?
It does, yes. Callahan and colleagues looked at weight gain over a longer period, a week, and sometimes even higher humidity. But the really distinct category they introduced is deliquescent.
Deliquescent, what does that mean?
It means the material absorbs so much water vapor from the air that it actually dissolves in it. It forms a liquid solution.
It dissolves itself just from humidity.
Just from the humidity in the air. Imagine like a salt crystal literally turning into a little puddle.
That's incredible. And you can immediately see how that would be problematic, especially going back to medicines.
Oh, absolutely. Hygroscopicity is a huge factor in the physical stability of pharmaceuticals.
How so? What actually happens?
Think about powders or granules. If they absorb moisture, the particles can start sticking together, caking, forming these solid bridges.
Right, like sugar clumping up.
Exactly. And that makes manufacturing difficult. Problems filling capsules evenly, pressing tablets correctly. It affects dosing.
So consistency goes out the window?
Completely. And it's not just clumping. The moisture can actually change the solid state form of the drug. It might go from a stable crystalline form to something else, maybe even amorphous.
And why is changing from crystalline to amorphous a big deal? Isn't it still the same drug?
It is the same drug chemically, but the physical form matters immensely for how it behaves in the body. A crystalline form might dissolve at a predictable rate, but if it turns amorphous because it absorbed moisture, it could dissolve way too fast or maybe too slowly. That completely changes absorption, bioavailability. It's a safety issue.
Okay, so physical changes are a major problem. But you mentioned safety. Does the water do more than just make things sticky or change their shape?
Yes, unfortunately. Absorbed water isn't just sitting there. It can actively participate in chemical reactions.
Like what?
The big one is hydrolysis. That's where the water breaks down the active drug molecule itself.
So the medicine becomes less potent.
Less potent, yes. And worse, it can create degradation products, impurities. So the drug might be less effective or potentially even unsafe. Plus, more moisture can sometimes encourage microbial growth, spoilage, basically. And tying back to the physical changes, if the moisture causes the drug to form hydrates or change its solid state, that directly impacts solubility and dissolution rate, how quickly it dissolves.
Which, again, affects how much gets into your system, bioavailability.
Exactly. It all connects back to how that drug interacts with moisture.
So wrapping this up, it seems like hygroscopicity, this tendency to absorb moisture, it's not just some obscure scientific property. It has really profound consequences.
Yeah.
For medicines, it impacts stability, effectiveness, even safety. It's like a hidden battle happening in the pill bottle.
That's a perfect way to describe it.
Yeah.
Caking, chemical breakdown, changes in how the drug is absorbed.
Yeah.
So many potential issues trace right back to how that material handles ambient humidity. It's fundamental.
It really makes you think. If something as simple and ubiquitous as humidity can have such a significant effect on product quality, what other, maybe hidden scientific principles are quietly influencing the things we use every single day without us even realizing it? Something to consider. We'll see you next time on The Deep Dive.